Okay. So, let's see what we have this time. We have a ball that's going to travel a distance of 1.66 meters. And it's going to be released from an electromagnet.
A ball projected horizontally causes a second ball to drop vertically, starting at the instant of launch.
Sorry. There's two audios. I don't know.
I like it.
Okay, let's watch it in slow motion. So we release two balls. Frame by frame. So you can see they've both been released. You can see one is starting to travel horizontally.
Again in slow Compare the vertical and horizontal motions of the two balls.
Note the positions of
they
the two
both
balls
have the
with
same
respect to the
vertical
point of
location
launch,
at equal times.
with respect to
they
each
hit
other,
the floor at the
with
same
respect
time.
to the floor.
Sorry, it should be, I can't get it to fix. Okay, so we saw in slow motion that they went at the same time. Okay, let's look at another example. All right, so we have a crossbow, and it is launched at a ball, and the ball is going to be dropped from the same height.
A ball is projected horizontally
made from the
at a
leaf of an
target
automobile
ball that
spring
starts to fall
is
the
used to
instant the
project the
projectile
ball in
leaves
the
the barrel.
horizontal
The
direction.
projectile
A
is aimed
switch
at
on
the
the
initial
barrel
position
causes
of
the
the target ball.
electromagnet to
Sorry, I'm just trying to get it to
drop the
Both
target
balls
ball
fall
at the
equally
instant
under
the
the influence of
projectile leaves
gravity.
the barrel.
The
Where should
horizontal
we
and
aim the
vertical motions of the
projectile to hit the
projectile are
target ball?
independent.
It's supposed to, it won't. Sorry, old technology.
How
If
do
the
the vertical
velocity of the
locations
projected
of the
ball
two
is
balls
great enough to
compare?
reach a point
Step
below the
through this sequence
electromagnet,
and
you
watch
will get
carefully.
a hit.
We'll just not listen to sound. So let's watch that again.
Sticks.
So we're launching the ball at another ball. And you can see that they hit at the same time down at the bottom because they both accelerate down at the same rate. All right, I got another example for you. All right, so in this example, an airplane is going to drop a flare, and you'll see that ignoring air resistance, the flare mostly stays under the plane while it falls because the flare is a freely falling object, while as the airplane is traveling. It's a little bit off because of air resistance, though, so you'll just have to think about that. Because in this case, the airplane just keeps on traveling with a horizontal velocity. The flare actually starts with an initial horizontal velocity, because it's part of the plane initially. And so it leaves with that initial velocity that the plane has. See? Flare stays under the plane the whole time. So our flare is like a horizontal projectile. The plane demonstrates how the initial velocity in the x direction remains constant, and they roughly stay under each other the whole time, with the exception of air resistance. And then we have one more similar example. So this is the snowmobile. This is similar to the plane, except now it's going to launch the flare vertically. So again, what should happen between the flare and the snowmobile?
Well, flare should be like above it, but at the same can say.
Yeah, the flare is going to stay above it because what do you know about the horizontal velocities? They're the same, whereas the flare will also start to go up and then down. Why? Gravity, whereas the snowmobile doesn't have to deal with gravity. There we go. So the flare started and ended at the same place on the snowmobile because it traveled with that same x velocity the whole time. It's the same thing as if the snowmobile had been at rest, not moving with an initial x velocity at all. It's the exact same thing. As opposed to when it's moving with a constant speed, again, it's going to start and end at the exact same place on the snowmobile because they have the same initial x velocity.
So technically, technically vertical and horizontal objects that are moving, technically they have the same velocity and acceleration, although for x, acceleration doesn't really exist, and for y, velocity doesn't really exist.
Do we have velocity in the y direction?
Initial velocity.
Say it louder.
Initial velocity isn't there. It's not velocity.
Right, your initial velocity in the y direction is 0, but will your velocity change in the y direction?
Yeah.
It has to. Why does velocity in the y direction have to change? Well, right, because we have gravity, we have an acceleration, right? So if we have an acceleration, we have to have a change in velocity. So does that make sense, Matt?
But then why?
Your velocity in the x direction does not change because there's no horizontal acceleration.
I mean, demonstrating the things we just saw, it seems like the y velocity should also be the same because it's moving at the same rate as x.
Doesn't it travel up and down? And it's just like a free fall problem, right? Where when it's falling up and down, it's moving at different rates. Like every second, its velocity changes by 10 meters per second. So it has to have a change in the y velocity because we have an acceleration. X velocity will not change at all.
Does this only work if it's like shot straight up?
Yeah, we're not looking at angles at all because if you're launched at an angle, can you say the initial y velocity is 0? No. So we're not going to look at launching things at angles. We're only going to look at horizontal motion. I think this is it. So again, you can see right there at the top, its velocity is 0, and then it starts to speed up as it goes down. So our y velocity is definitely changing. Our x velocity stays constant.
Is the reason that you couldn't say it would be a 0 initial velocity if it was at an angle is because it has a certain direction instead of being vertical?
Yeah, so think about, I'm going to stop this.